Watch a crashing wave in slow motion, and you are looking at one of the most complex phenomena in the known universe. To describe this water mathematically, you must track every fluid particle moving simultaneously along the x, y, and z axes. Every drop has its own velocity, pressure, and direction, constantly colliding with millions of neighbors. Attempting to solve for every individual interaction in a citywide plumbing system would require calculating trillions of variables, a level of detail that is functionally impossible to process for most engineering tasks. Instead of chasing that level of precision, physicists and engineers systematically strip away the spatial dimensions that are least relevant to the final result. Classifying flow as 1, 2, or 3-dimensional allows us to transform these overwhelming real-world scenarios into solvable mathematical models. One-dimensional flow is the simplest version. Here, the fluid's properties only change along a single line. Think of cars stuck in a single lane on a highway. You only need their position along that road to determine speed. Movement in other directions is effectively zero. When an engineer designs the water mains for a high-rise, they treat the water as a uniform block sliding through the pipe, ignoring the minor variations happening near the walls. There is a classic trick used to catch new students off guard. If a pipe bends into a giant U-shape, the water physically changes direction, but as long as it is confined to that single route, it is still a 1D problem. Because the fluid's pressure and velocity only change relative to the distance traveled along that specific center line, the math remains one-dimensional, no matter how much the physical path curves. When air strikes a wing, it splits, moving up, down, forward, and back across an x and y axis. If the wing is straight, air behaves identically along its width. By focusing on a single flat slice, we delete the third dimension entirely. It is like watching a marching band from a drone hovering directly overhead. You can track every formation change and sidestep across the field, even if you can't see the height of a single musician. This 2D approach allows designers to test complex aerodynamic shapes and predict lift without the massive workload of tracking every air molecule across the entire span of the craft. Of course, some systems refuse to be flattened. In 3-dimensional flow, fluid properties shift across all spatial axes at once. You cannot compress the erratic rotation of a tornado into a straight line, and you cannot view the churning of blood through the chambers of a human heart as a simple flat slice. These irregular geometries demand full 3D analysis. Engineers choose their model based on specific needs. 1D is for city plumbing, 2D helps shape the curves of a car's hood, and 3D is reserved for critical, high-complexity environments, like the inside of a rocket engine. Once the geometry of the space is defined, we can finally analyze the forces acting within the fluid itself. This sets the stage for the next layer of classification, the dynamic competition between a fluid's momentum and its own internal friction. Advanced fluid mechanics relies on this strategic omission, using the minimum number of dimensions required to capture the physics that actually matter.